Should you aim for a CPK of more than 1.3? And why? Yes or no? So what's sort of the story about that 1.3, 1.6, whatever? Hello, I'm Tom. Welcome to my channel where we talk about continuous improvement in an industrial setting. And today's video, it is about CPK limits, basically, right? So I had this video on Cpk and Ppk, process capability, and one of the comments was, but why this 1.3 limit? Because, you know, much of industry is happy enough to just get it to about 3 standard deviations, or even less, have maybe 1 or 2% defects and be totally happy with that. Going higher just takes you away from profit, or it's too difficult. So why is this whole world-class 1.3 thing in there? So let's have a bit of a discussion on that. And I will start the discussion by saying, look, you don't need to follow these guidelines. It is a management decision what level of process capability you want to be at. I also do not really believe in the idea of having a CPK of 2 as in a general standard. It is very high indeed. And I think it's more than needed high. But there is merit to having a Cpk and a Cmk of definitely more than 1. And let's talk about, where this comes from, why you want to have it. And we'll start with your sort of end result is you don't want to make defects and scrap, right? But especially the defects. And the idea is if you have your specification tolerances and you have a process that has a certain standard deviation or a certain degree of variation in its output, then we sort of say plus and minus 3 standard deviations, that is 99.7% of your process output, that is your whole process. That's why you usually see these Gauss curves being drawn with plus and minus 3. If that hits your specification limits, then we are talking about a capability of 1. And so take the range, take the deviation in your process, then divide it either by 6 or divide it by, if you only look at one side, so that's with or without decay. So without decay you do 6, and you don't really look at the centering. With decay you take to the closest side and you divide by 3. You divide 3 standard deviations by 3, then you get to 1, right? So this is 1. Now we also should know the difference then between the process performance, the process capability, and the machine capability. See, the thing is, it's in the way that you measure them. Process performance, it takes your big sample, you sample over preferably multiple days, and you take all of your data points over different operators, different material batches, maybe the machine has had some corrections, it's a different day, things like that, right? So you take quite a bit of process variation into account, take all of that, and you calculate the standard deviation of your output over that whole production. This means that you, in your calculations, include your actual performance. That standard you want to have sort of at least at 1. And why at least at 1? Well, that way your whole process at least fits within the specifications, and you have already taken into account that people sort of adjust the process a bit, that you change your material batches a bit, that you change your packaging. Well, there's a whole bunch of things already happening. So here I do agree with the commenter that maybe 1 is already good enough, because a lot of variation is in there. Now, the process capability has a different way of calculating. See, here what you do is you take subgroups. So also over a bit longer time you do have the material changes and stuff like that, but you take subgroups, and subgroups means that you take a number of samples relatively quickly, one after another, then you average them out, but you also look at the range. So you look at what is the variation between them. If you take a bit larger samples, you can take the standard deviation of each subgroup. If you take smaller samples, you take the range and then you divide by a D2 coefficient to estimate the standard deviation. What you do here is you take a number of subgroups, over a longer period of time. But remember, each subgroup has a small period of time, and you check what the variation is over time in your process. But if it does like this, every time that small variation is sort of the same. So what you're checking is, would your process be capable, also after you change an operator, with different operators, with different material batches, would your process be capable of being within the specifications? But we're not looking at where the actual value goes. So if your whole process shifts a bit the whole time, then that part, the shifting part, you're not taking into account. Which means that there is a big variation part, the possible drifting or shifting of your process mean, that is not in there. So what happens between Cpk and Ppk, so to say, is that you can have drifts. And so it's the same size, but it drifts. And if it also drifts down a bit, then in the end you end up with something like that. This will still create defects. Now, because we know that you cannot control your process, to the second, as soon as it starts to drift a bit, you need a couple of values at least to understand, oh, we're drifting. This is not just a random sample here. No, this is actually the whole process is drifting. It takes time before you can react, before your operators can react. So you need to put in a bit of buffer there. That is why if you have a Cpk that is at least 1.3, higher is better, but more than 1.7, 1.8 is also not really needed. But if you have a higher than 1.3 Cpk, you at least have a bit of buffer space to be able to control that process drift in time, so that you still end up between the lines. Now, the machine capability, the CMK, that is even tighter. Well, what you would like is even tighter. Why is that? Because, again, the way we measure it, CMK, we take 30 consecutive samples, and that's it. So we set up the machine in the best way we know. We have a good operator there, whom we do not change. We have a material batch that is within specs, that we also do not change. So nothing changes. We take 30 samples, one after another, check what the difference is. That is the capability of the machine itself. So we've eliminated a lot of possible problems. And that is important to know. So here we actually expect even larger shifts to still occur, so that between what we measure with machine capability and what will be the process performance in the end. That's why in the textbooks you will usually find that a CMK should be 1.67, right, or 1.7. Now, where do these things come from? They are sort of linked in those 1/3, right? You sort of feel that already. When we know that these are, like, the arch is 3 standard deviations. Here, so the arch is plus and minus 3 standard deviations. You see that we hit the specification limit. So the specification here is also at 3 standard deviations of this process. So of course we're not gonna set the specification limit to 3 standard deviations per se. It's the other way around. We hope that our process, or we make sure that our process is stable enough to fit within. But here, there are 3 standard deviations between the average, the mean of the process, and the limits. To get to that 1.3, what we need is there to be 4 and minus 4 standard deviations. So when you have 4 and you divide that by 3, you get the 1.3. And that's also what you get here. A 1.67 is that you have 5 standard deviations, at least between your process mean and the limits. Basically, every time you sort of take one extra standard deviation and you call that your wiggle room, because operators react sometimes a bit slowly, or because you introduce more variation sources and it's just difficult to keep everything centered. Now, why do you see a Cpk advice of 1.67 or 1.7? That is because there is this, and it's a highly debated within more the statistical circles, there is this concept, or this, it's not even a concept, it is a group of thought leaders, group of people who assume that you need a 1.5 sigma shift, 1.5 z shift, to happen before you can really see it pop up in statistical process control. It is not for nothing highly debated. It's a good rule of thumb, but it doesn't have any real statistical basis, because even a small shift, if you just let it go on long enough, you will detect it, and a bigger shift you will detect more quickly. So it's like, But that is why you see that. So if you accept this rule of thumb that you need a plus or minus of 1.5 sigmas, 1.5 standard deviations before you can react, then you would want 3 plus the 1.5. Now 4 isn't even that yet, so you need 4.5. What is 4.5? It is a Cpk of 1.5 exactly. Why people do not recommend 1.5? It only has to do with these. For some reason, people want to stick to full sigmas. Makes it easier, so I don't know exactly why, but that's why you see these two. Because some people say, yeah, but 4 sigmas doesn't cover the extra drift space you need before you can, so your reaction time basically, that isn't covered by it. You should go to 5 sigmas immediately. That's why you see it. Is it good or bad? I cannot really tell you, but this way at least you know where the 1.67 comes from. So that's why you will see Ppks, you will see that they should be larger than 1, or, so more the purists, so to say, they will go for, let's make it larger than 1.3, because that way you definitely know you're safe. For Cpk, it is either larger than 1.3 or larger than 1.67 or 1.7. The ones that tell you it should be more than 2, I know, ideally, maybe. I will get to why you don't want it. The Cmk, yeah, that one you really want to have at least larger than that 1.67. Again, larger than 2, maybe, but well, depends a bit on your process. Now, why would you not want to have it even higher? There's basically a couple of reasons. The main reason is it is expensive to have a process that capable. Right? Making a process very capable, it's super. Right? If you can make your process more capable, do it. But generally, making it more capable requires improvements that really require effort, investments, maybe more expensive materials, more training. So there are costs involved in creating a more capable process. Now, if you put those costs in, there's basically 2 other things you can do to make more money than to aim for a system that has a performance, a process performance of much more than 1. Say, you can change the specification limits, or you can change the center. So if we have a very capable process, we can go to market. And what we can do is we can take our specs and we can tighten them, because if we can tighten the specs of our product, customers will love it. Even if they don't really need it, they will love it, and we should advertise with it. And we should say, look, we can give you that product with a very minimum tolerance. We can make it exactly as you need it. If your competitors cannot do that because their process capability is still, relatively poor as it used to be, now you get an edge over your competition. Either they follow with these specifications and they will be producing lots of defects, or they cannot follow with these tight specifications and you can use it as a part of marketing to sell your product, your production process. Or we go to a limit, and sort of an economic limit. So if we see, and let me just do this one in something else, purple or so. If we see that we are doing this, then, and we also know that this is super expensive and this side is cheaper, then what we will do is we will move the center of our process on purpose. Now, here I drew everything centered, right? That's for the Ks. So you have CM, you have CP, you have PP, and you have Cpk, Ppk, Cpk and Ppk. Got another video on explaining all of that, but the short of it is, if this nice form is here, like it is right now, it has the same Cp, but this we look at where it is here, and we say that Cpk, which takes into account the centering, here is even less than 1, right? Because it even goes outside of the limits with our 3 sigmas. This only has about 2.5 sigmas in here, so we get to a 0.85-ish. That is what happens with that K. Here also, if we have a process that has a good process performance, and we say, well, but we know we can do this. We could do that, but market doesn't want to really pay for it. In fact, we know that only one limit is really expensive, and you see this a lot with, for instance, packaging weight. If we produce milk and we need to fill our cartons with 1 liter of milk, we usually have only one specification. The government and supermarkets and what have you will say it needs to be 1 liter minimum. So if we have a process that's very capable, we can just creep closer to that liter. Or if you have a specific amount of aluminium in your mix or gold in your mix, going down is more economic. You don't want to go down too far because you'll be creating a lot of defects, which costs money as well. But this is also a reason why, if you have a process performance of really more than 1, so if you get above 1.3, start thinking which of these solutions to use. So I agree with the comment that the process performance results of, guidelines of 1.67 or 2, no, don't go for it. Unless this doesn't cost you anything in the market. But even then, right? Try to sort of force it into the market if your processes can do this. But if you have so either end costs you less, it is way too expensive to be sustaining process performances of over at 1.3 level. So I hope that it didn't muddle the discussion too much. If you are, and this is maybe important as well, if you are new to Cpks and Ppks and to this type of process thinking, go through the other videos first. Make sure you understand what we're calculating here. This is advanced stuff, but it will generate money for your company if you do this in a correct way. So I hope that shed some light on the comment, or maybe questions you would also already have, and on not blindly following all of the world-class standards that you see out there. If you did, don't forget to hit that like button. Also, I have a course on SPC, which can help you reduce variation. I have a nice course on gauge R&R that will help you measure the variance in a good way. All tools linked to this system. Go check them out on my website. a couple of nice propositions for you, and that will seriously support this channel as well. For now, I wish you the best of luck calculating the performances of your processes, and as always, don't forget to also enjoy the continuous improvement journey.